The next path attribute, which we are going to use to influence BGP path selection, is MED, or multi-exit discriminator. It works similarly than AS path. We send it outbound to a neighbor so that we can influence the path selection of the neighbor AS. In this example, we want to get to router 4 from AS 65001, and we have two links available to reach AS 65004. One through router 1 and one through router 3. And let's see which one do we use by default. On router 1, for example, show IP BGP. On router 1, we use this link between router 1 and router 4. And the next hop is router 4. So why did router 1 choose this path? So there is a tie in weight. Both of them is 0. There is a tie in local preference. Both of them have the default value, which is 100. Although this is not displayed here because it is an eBGP peer. Neither of them are locally originated. The length of the AS path is the same. The origin type is IGP in both cases, so the prefix was advertised with the network command. The MED has not been assigned to neither of them, and that is what we will be changing shortly. And if we can't decide based on these attributes, the next rule simply says that prefer eBGP peers over IBGP peers. Router 4 is an eBGP neighbor, while router 3 is an IBGP neighbor. So that's why we choose router 4. Similarly, on router 3, show IP BGP, router 3 chose this link because of the same reason. An eBGP neighbor is chosen over an IBGP neighbor. What's the situation on router 2? Show IP BGP. Router 2 can't decide based on this attribute because both of the neighbors are IBGP peers, so it goes further. It checks the IGP metric to the next hop, so the OSPF cost, which is again the same. These are gigabit links, and I didn't change the reference bandwidth. The IGP metric is not displayed here, but we can verify it. Show IP BGP and the prefix metric 2 and metric 2. This is the IGP metric, so the OSPF cost. This metric is the MED, the multi-exit discriminator. It is 0 by default, so it can be a little confusing at first, but these metrics are completely different. In this case, there is also a tie in IGP metric, so router 2 simply prefers the lowest router ID, which is router 1. Now, what we are going to do on router 4, we are going to assign a MED attribute to the prefix 4444/32 and advertise this NLRI with different MED values to each eBGP neighbor in AS 65001. let's say we advertise this prefix with a med of 10 to router 3, or med equals 10 on this link, and with the med of 20 to router 1. And the lowest med is preferred, similarly to the IGP metric. And med will be transitive within the neighbor AS. So router 2 is also going to choose router 3 instead of router 1. But med is only going to be transitive within this AS. The med values of router 4 won't be forwarded to AS 65007 and to AS 65005. And we begin by matching the prefix with an ACL. So let's create an ACL on router 4. Access list 1 permit host 4444, and we will need two route maps because we have to apply different route map to each neighbor. So first route map med to router 3 permit sequence number. This will be used on router 3. Match IP address 1. This is the ACL we have created before. Set metric, and this is the med. So let's use the value of 10, and that's all. And we will need another permit statement for every other prefix because of the implicit deny. So route map med to R3 permit, and we increase the sequence number, and we create another route map for router 1. Route map med to R1 permit 10, match IP address 1, set metric, and this should be higher than the previous value, so that AS 65001 will prefer this link towards router 3. So we need higher than 10. Let's use the value of 20. And we need another route map for every other prefix. And we apply the route maps to each neighbor. Router BGP, the AS of R4 is 65004. Neighbor 10041. This is R1. Route map med to R1, and outbound, similarly to the AS path prepending, we send the prefixes outbound towards the AS 65001 with the changed med attribute. And the other neighbor and we resend the prefixes. So do clear IP BGP out, so that the attributes will be changed in AS 65001. And let's verify on router 1. Last time we preferred the direct connection to router 4, and now show IP BGP. The next hop is router 3 because of the lower MED value. Similarly, on router 2, show IP BGP, the MED is forwarded to router 2. So now we use router 3 as the next hop. And also on router 3, show IP BGP, we use this link. And here is the packet capture of the BGP update message, which router 4 sent to router 1. Here is the prefix under the NLRI 444/32 and the path attributes. Here is the MED, which we have assigned to this prefix. It says that non-transitive. This means that the MED is forwarded to the neighbor AS or to AS 65001 and to all routers within AS 65001, but the neighbor AS won't forward it to its neighboring autonomous systems. So for example, router 7 won't receive this path attribute. So let's verify on router 7, show IP BGP. See, this metric column is empty, so it defaults to 0. So similarly to the AS path prepending, the MED can be used to influence the path decision of the neighbor autonomous system. Now I'm gonna delete the route maps to the eBGP neighbors on router 4, or do show run pipe section BGP. These are the two neighbor commands which I am going to delete. I'm gonna simply copy it and remove the command with the no keyword and the other one as well. And reset the peering, do clear IP BGP. And now we have the same situation on router 2. There is a tie in everything basically, and we prefer the lowest router ID, which is router 1. Now let's configure router 2's path selection with the IGP metric. So if the weight and the local preference are the same, the route is not locally originated, the AS path is the same, and the origin code, both neighbors are IBGP peers. So if there is a tie in everything so far, we can still influence the path selection with the IGP metric, so the OSPF cost. From router 2's perspective, both links to router 1 and router 3 have the same cost, the cost of 1, because the reference bandwidth is the default. Or show IP route OSPF. See, both router 1 and router 3 have the same cost, which is 2. If we change the cost of this interface, interface gigabit 0/0, the cost to reach router 1 will be higher, so router 3 will be preferred. So let's verify that. Interface gigabit 00 IP OSPF cost, and we need anything higher than 1, so 10 for example. And let's check the BGP table. After some short time of convergence, router 2 now prefers router 3. Because of this reason. The IGP metric is lower in this case. To reach 1111, which is router 1, we have a cost of 3, because this link has a cost of 1, this link has a cost of 1, plus 1 for the loopback interface, so this equals to 3, while the cost to router 3 is unchanged. So router 3 is preferred. So in certain circumstances, we can also use the IGP metric to influence the BGP path selection.